My name is Esfandiar Kuhi, and I'm the Simulation Product Manager at Intercad. This is the first seminar of the series. As you can see, the topics we're covering is first starting with the finite element definition, and we will introduce the interface of simulation tool in SolidWorks and the options available. With the case study, we will have a simulation pre-processing procedure fully explained of how to create a study, how to apply material, fixtures, external loads, and meshing the model. We will solve the model and we will go through the post-processing stage as well, the options you have in post-processing and how you can make some, let's say, tailor-made graph in SolidWorks simulation. And at the end, we will also introduce the range of the seats available in SolidWorks simulation, where that would be a very good guide. Depends on your application and your usage. You can select any of these seats and then come to us to provide you the license. Okay, now let's first start with the definition of the finite element analysis. Just imagine a case that we would like to measure a brick road coming from home to a mailbox using a yardstick. This is the curve path we have, and we would like to use this tool to measure this distance. The curve path is broken into straight segments, and length of each straight segment is measured by yardstick. These lengths are added together to get the final length of the curve path, like we're putting our yardstick start, end, and we approximate this curve by that yardstick. Now, depends on the size, we are going to approximate the curve by assuming the curve is represented as a straight line. Now, if the yardstick is small enough, we have more accurate representation of the curve. However, it will take a long time to do the final measurement. On the other hand, we can use the bigger tool. It will finish very quickly, like 1, 2, 3, and our estimation would be very rough. Therefore, depends on the tool we use, we can have a good estimation or a bad estimation. It could take long or short. This is exactly the case when we do a simulation. As the major step in the simulation, we are going to represent the actual geometry of the part or assembly we have, which we call it model, with some standard tool, which we call them elements. So the elements are going to fit into the curve path and the whole part to represent its 3D geometry. The elements could be on a tetrahedra or triangular shape, and they may share at some point. And these points are what we call nodes. And the network of this element connecting together is simply called mesh. So what we do in a finite element, we put a measure tool like an element where the shape is tetrahedra or triangle. Then all this together will represent our let's say geometry. The connection points are nodes, and then we applying our boundary condition, the physical condition of the part, like force and everything else. And then we start the calculation on each point and solve the whole domain relevant equation on each node, and then solve the whole domain. The outcome could be the stress value, the displacement value, and the other specific values you like to have. So finite element is about an approximation of the CAD geometry with the elements, where the elements are the measuring tool, and we have the ability of calculation node by node, means point by point through all elements. So after this, we would like to show you the standard procedure and the steps involved in preparation of an FEA model in this slide. The steps are simply divided by 4, which first is your CAD design, where you do the design in your CAD software. Then we have a pre-processing, then we have a solution, and then post-processing, where you see the whole result. So more in detail is where you decide to design on a CAD geometry, but when you're trying to put it in FEA solver or FEA modeling base, you can do some simplification. For example, as you can see in this figure, these fillets on the sides been eliminated, as they are not play an important role in FEA, but having a curve shape will add some complexity to the meshing system. Therefore, we can do the simplification, but this fillet, where we're expecting a lot of stress concentration, will remain there as one of the main features. Therefore, the first step is the design, and then do a right simplification to our CAD geometries. After this stage, we are starting the pre-processing step, and where in this step we preparing our mathematical model. As a first part, we have to understand what type of analysis is suitable for our problem. Is it a structural analysis? Is it a static analysis? Is this a dynamic one? Is it a flow analysis, heat transfer analysis, and etc. When you found out about this, then we are going to the next step, where we are assigning the material to our actual geometry. Material properties such as Young modulus, Poisson ratio, tensile strengths, yield and strengths is what we are assigning on the next step. After this would be the connection of our actual model to the real world. This is going to be defined by series of support we're putting on the boundary of our model. And next is the physical condition, which is loads, pressures, and everything else which imposing displacement, deformation, or any motion. Since we do the preparation of mathematical model, then the next step is to discretize the model, means mesh the model, where we specifying the shape, size of the element to go through the whole geometry and represent. So basically, loads and support are, some of them are applying on the boards, on the nodes, on the boundaries, and the rest is using that input data, and the solver will get that input data and solve through the whole domain. This is where the third step is coming through. So FEA solution, where a numerical solver will solve the equations, the appropriate equation, through all elements. Since the solution is being finalized, now we are in a stage of post-processing, where we can review our result, which could be stress, strain, displacement, and etc. We can prepare some graph and also make a probe and magnify the critical area for further revision. So this is the general overview of building an FEA model. Let's have a closer look through the actual steps here, where the first one is talking about the fixtures. Fixtures represent how the given model is attached to the rest of the world. For instance, if you have a look through this assembly, there are so many parts are attaching to each other. But if you are interested to just analyze that part, we can take it out and bring the impact of the other parts by applying series of fixtures. For example, fixing a surface, edge, or a point. Allow translational, sliding, or rotational movement on this part. This is all going to do to achieve one important fact. We are trying to reduce the size of the problem to a component level or sub-assembly level. And that's why, because more parts we have, more complex problem and more simulation time is required. So we're trying to minimize our time and maximize our, let's say, accuracy. So one very important step is how we define the fixtures. Next is how we bring the actual boundary condition to our mathematical model. This could be done by applying series of load. For instance, if we have an assembly like that and we have a bearing, the loads on a bearing could be in terms of pressure, tensile load, compression load, where all these could be applied to surfaces, edge, or points. They could be in a form of torque, moments, and pressure. And there would be some loads which going to applied on the whole assembly and model, like gravitational force, centrifugal force, or thermal loads. Next is, as we described before, is how we discretize the model, how we describe our actual 3D, let's say, geometry. If we have a solid model where appropriate dimensions are there and thickness, for example, a fitting, we can split the fitting into small tetrahedral pieces and approximate the deformation on each piece. In this case, the elements could be as a draft quality, where we have 4 nodes and 6 connection lines. Each element is going to put on the whole structure. Or if we like to have higher quality meshing, so we put higher quality element, where this is 1, 2, 3, 4 side node, 1, 2, 3, 4 middle nodes, and 2 top and bottom nodes. So more points to calculation, more accurate result, very time consuming. Less point to calculate, rougher estimation, but fast calculation. Next scenario is for the series of the parts, where like a sheet metal parts, or let's say the parts which their thickness compared to the other dimensions like length or diameter, which is very, very small. As an example, this bracket, as you can show, could be splitted the surfaces of the bracket into small triangular pieces and approximate the deformation on each piece. This element type is called shell element, where for the draft quality we have 3 nodes, 3 connection line, or we can have 3 nodes on the sides and 3 nodes in the middle, which is high quality. So up to this point, what we said, solid will use the tetrahedral elements, and also we have the shell elements, which is triangular shape. And the next type of the elements we can put for the main measurements are the beam elements. For example, if we have a frame structure, we can split the member of the frame into small straight pieces and approximate the deformation on each piece. That will make the problem more simpler. Now, it is very, very important to understand which one is correct. If the assumption of using solid elements, shell elements, and beam elements are correct, and we are not sacrificing the accuracy of our calculation. But we have these 3 options to do the meshing and represent our geometry. All right. Now, since we have the setup, we have to understand what we need to know and what we need to measure to validate our design. So basically, one of the major, let's say, properties we are always evaluating is stress. You can see in the picture, stress at the point are defined by 6 quantity. 3 normal stress, Sx, Sy, and Sz, and 3 shear stresses. But the question is, do we need to know all these components at once? Or there is a way to know an exact value at a point, and we can decide if the material at that point with that level of stress failed or not? The answer is yes. 1 Mrs. stress give us one number that is typically compared to uniaxial tensile strengths of the material. As you can see in the formula, all the components are here. With some mathematical operation, you get an equivalent stress as a point. We also have the other criteria like principal stress, where it's talking about just 3 normal stresses, where they are specified in a spatial coordinate system, and at that point or at that angle, the shear stress are 0. Now, when we found that what is our actual stress on a point, we would like to know, based on our material, if our design is safe or not. Is it fail or not? So we come to the definition of factor of safety, which is the ratio between limit stress for the material, how much material can tolerate, to maximum 1 Mrs. stress in the model. So if this ratio is less than 1, means maximum 1 Mrs. stress on your actual model is more than its limit. Therefore, the part is failing. If it is exactly 1, then we are on the border. If it's more than 1, then design is safe. So this is the main thing we do the check after we solve the model. Now, after that point, there are some assumptions and common terminologies usually we're hearing when we are reviewing an FEA, let's say, problem, like the assumption in linear and static analysis. Now, let's have a look a little closer at a couple of these assumptions. A linear system displays a response that is directly proportional to the applied loads. As you can see in this picture, we have a linear relation between force and displacement. Between force and displacement, we have a linear relation. That simply means the displacement and stress at a load of 100 kilonewton is exactly 2 times larger than the displacement at stress at 50 kilonewton. This comes from the fact that the stress is considered to be directly proportional to the strain. And also we adding the fact that deformation on the structure is very small compared to the dimension of the part. Second is the material linearity, material linear elastic. The elastic material assumption means there is no plastic deformation and the part returns to its original shape if the load is removed. Simply, you applying load, for example, bend a plastic part, if it's getting back, then we are in a linear region. However, if we have a case like a situation like bending a sheet metal, where the amount of plastic deformation determines the final bend shape, we can't analyze with an elastic material because we are going to permanently deform the shape. So that is the second point. And the third point is about load and static load. The static load assumption means that the loads are applied slowly enough for the inertial effects to be insignificant. Therefore, any fast loads, like when you do a drop test or striking a nail with a hammer, where we have the amplification of the load because of the speed, are not the case of static loads. So three major things we covered here: linear analysis, where we have proportional rates of force and displacement; linear material, where the material is getting back to the original position if we remove the load; and the third is how fast and how slow we apply this load. So all of these assumption and, let's say, description, we're getting to that to distinguish what sort of analysis we need. Therefore, if we would like to have a FEA, let's say, simulation in SolidWorks or in any other software, there would be some certain, let's say, checklist. First, if you have your geometry design and simplified. Second, we have to assign the material and decide what material is going to use with some property, with any properties, like, for example, you specifying yield strengths, position ratio, elastic modulus, and etc. When you have assigned this, then next stage is to work out about the physical condition, or let's say boundary conditions, where we're specifying the type of loading happening here. For instance, we have pressure, force, moment, centrifugal, gravity, or all of this case together. And next stage is to see how our actual model is related to the real world. For example, do we have a bolting, or we have welded the whole assembly to the environment? Now, at this stage, we have prepared our, let's say, model. And then after this point, we need to be trained for the specific software. For example, if you're talking about the SolidWorks simulation, there would be a training required about how we set the parameter and how we can translate the parameters and the physical condition to SolidWorks. As you can see in the picture, for instance, this is the communication menu we have when we specifying the mesh. When we solve the problem, we can have an overview from our result and find out if our design is okay. Reviewing the result in terms of stress, strain, deformation, and factor of safety will give us the answer of yes, no, development, modification, and etc. So these are the, let's say, steps, and let's go and have a case study. We will practice all this concept, as I've explained, with some focus on the ability of the SolidWorks simulation software in a case of stress analysis of a flat plate, as you can see in the picture. This flat plate has a hole inside. It is restrained on one side, and it's under, let's say, tensile load on the other side. We will review the options in the SolidWorks. We'll review that how we choose the study, how we select the material property, apply restraints, load, and mesh, and run the actual study. And also we will introduce the influence of mesh density, means we have coarser or finer mesh, and how we will see how it's affecting our final result. We also have a brief overview of post-processing options we have in SolidWorks. All right, so let's bring the case first and find out what the case look like and what the simulation software can do for us. So simply, if you the interfaces look like what you usually experience in CAD, you simply open the model, and the model is now here. In your, let's say, command manager, you can see the simulation tab here. If you have the correct licensing, this is the tab, and you can activate it from Adds In and going to SolidWorks SolidWorks Simulation ticked, and click OK, and you have this tab. Now, in order to initiate this study, you have this option when you are in this command, and simply you're going to have a study advisor if you have no idea, or you can start a new study, and here is the next communication box. You can name this as static, and there are range of study you can choose. I would like to mention this depends on the license you have for simulation. So the basic license is coming with the static analysis, and the more advanced licenses you get these options active or deactive. So static is what we choose, and then click OK. Now when you're clicking OK, you can see your interface is changing. You have your feature manager here active, and you have new features are adding to your interface. First is study 3, where you can see the part is here. You can define connection, fixtures, external loads, mesh, and result options. When you do this, your actual toolbar is getting active, where you can put different inputs and define different output from the commands you have here. Always click on Study Advisor. It is coming with more hints and help for you at the right side, and you can decide to take the advice or do it yourself. Okay, so this is the interface we have. Now let's start with creating an FEA model. Now the first step, as we said, and as you can see in a design tree, is how we applying the material. If we right click on the part, and you can see there is a communication box, you have apply edit material. Clicking on this will bring you a next communication window, where for the default is selecting a material from SolidWorks library in a steel category. Have a closer look. We have very well prepared number of material in the SolidWorks material library. Steel, iron, aluminium alloys, copper alloys, and etc. Rubber, silicon, and on each category there are some material listed. Or even if you like, you can have your custom material and you're creating new one and you apply the material properties there. So for our case study, we selecting ISI 304 as a steel one, where you can see in the next communication box, the model type is linear elastic isotropic. The units is SI. You can always change this to any units you like. And these are the list of material property like elastic modulus, cohesion ratio, shear modulus, density, tensile strength, and etc. You can have this material modified if you are creating a custom material for yourself. Okay, now clicking on apply, you will get a very important feature appearing. There is a green tick box on your material model, where it's saying ISI 304 is assigned to your actual model. So material definition is being finished. Now, next step is how we fix our actual model. This is happening on the fixture section, where if we simply right click, we have some options here. We can have the advisor active, or we select fixed geometry, roller slider, fixed hinge, elastic, and etc. Or we have advanced fixture. Let's select the fixed geometry. The very good thing and very good capability here is when you're selecting a type of fixture, it will animate the real case scenario of how it's acting. For example, if we're selecting this face to be fixed, it will show you the face is not allowed to rotate, slide, or translate, but the rest of the model can do that. If we switch to roller slider, it can show you the model will slide on the actual face selected, but it won't move. Or in the case of fixed hinge, this is the case scenario where we have translational movement allowed. We can have an advanced option where again we have different options to use the selected reference geometry, put it on the flat surfaces, cylindrical surfaces, and spherical surfaces, selecting the faces, and then specifying in which direction we would like to make this free to move or restricted to move, or have a prescribed displacement on it. So get back to the standard, and for this specific example we click OK on the fixture. Zoom in, you can see all three directions of the move is being restricted. Okay, so we have defined how this part is get connected to the real world. Next stage is how we apply the load. So right click on external load. Still we have the advisor option, but we have force, torque, pressure, gravity, centrifugal, bearing load, and temperature. Also we can bring flow effects and thermal effects if we have flow and thermal studies in a different software, and bring it here. Click on force, then we simply can go and select the face we would like to apply the force. We can select it is normal to this face or normal to direction. For instance, if I choose this, the direction of the force would be like that. If I choose normal, it would be normal to the face. I can also reverse the direction, and I can specify the magnitude of the force at any time. So 11,000 Newton normally in the direction as shown is what we select, and we click OK. Okay, so up to this stage, part is fixed, load is applied, and now we're ready to do the next stage of do the meshing. Again, right click on the mesh. We have list of options applying available. Now if we click on create mesh, it is very simple communication box first appearing, where you can just simply slide between a very coarse mesh or a very fine mesh. That is a very rough estimation if you like. Anytime if you don't like it, we can reset. But we have more advanced option to make some meshing and element sizing more specific to our model. Standard mesh will consider an element size, a global size, and it will go through the model. However, we have more advanced automatic measure tool where we can specifically define the maximum element size, the minimum element size, and also the minimum number of elements in a circle and element size growth ratio. Simply, maximum and minimum is what you assign, and the auto measure tool depends on the different feature on the let's say model, will adjust the element size to fit high quality mesh everywhere. Minimum number of element in a circle defines how the small feature in a geometry will be resolved. For example, if the model have a hole, the number of elements in a circle will define how many elements will surround that circle. So we're saying 8 elements around the circle. And the last parameter we're talking about is the ratio, which is used to define the transition of mesh from the minimum element size to maximum element size. How smooth or how fast the mesh is growing. Okay, so in our case, we are happy to use the default setting and then clicking OK. You can see the automatic measure tool now put all the elements, as you can see in the figure, and this is how the geometry is being presented. All right, now the model preparation is now finished. We are ready to solve the domain and review the result. This option could be simply achieved by clicking on Run, and you can see as quick as possible the model is being solved. Now, there are some standard results we can review, like the stress one. You can see in some let's say regions we have the stress value shown here. What I would like to do is to modify my load and go back to edit definition. And make this 10 times more to get a more range. All right, now first item is the stress result. You can see the maximum stress are shown by red region, and we have a rainbow color pattern from minimum to maximum, and then yield strength is shown here, where from that point we simply pass the yield strength on the model. Means it is not a linear problem on the region which they have the stress result beyond this value. You can see we have a high stress value here, and also the study will telling us the part going to fail at that point. But the question is how we can define this. If you right click on the result, you can define a stress plot. You can select one misses, you can have principal stresses, or you can have normal stresses. You can specify the actual units, and for advanced option you can use nodal view or elemental view. The deform shape is coming to automatic scale, could be a true scale, could be a user-defined scale. Where if you're reviewing what we have here, by go to edit definition, you can see it is one misses stress, it is the nodal value, and automatically been select how to show your deformation shape. If I click on true scale, you can see it is in reality like this. But in order to magnify this for you, if you go to the automatic, it says 139.41% larger. So click OK and you have this. Same scenario we have for displacement, simply showing us 0.1435 millimeter of displacement here. Also, we can review the strain results and see what are they look like. One of the good options we have, if we right click, we can go to the chart option and make this let's say chart more specified or tailor-made by selecting show minimum and show maximum. The software will add 2 more tags on your actual result plan, and it will show you where the maximum is happening and what is the magnitude, where the minimum is happening and what is the magnitude. Also, you can control the position and format of the legend by saying I would like it as a floating, general, scientific, or you can say I need a thick, thin or normal legend. The other option is the setting option. where we can choose to have continuous legend or the secret region on the actual model. So simply the secreting model on the secreting presentation of the result on the actual model you can see here. It could also show you on the model or on the mesh, where the mesh is here and you can view your result. If you're clicking on superimpose model, then the original shape of the model will appear and you can simply have a comparison what it was look like and now where it is with the magnification. Also, we can have some specific, let's say, stress, strain, or displacement, let's say, plots, where if we go to, let's say, section clipping, it will ask you, I will section your actual model based on the front plan, or if you like to change it to the top plan or the right plan. It could have some degree distance from the main one, and it could have some angle inward and outward. And then simply you can show the result and focus your presentation here. The other interesting tool we have here is when you do the probing of the results. So if we go to that section and click on probe, any place of the model you can put your probe and get that tag add to it. So I would like to show this region or that region. So all the nodal values are listed, the value is here, and it will provide you a summary of these with the value of what is the summation, average, maximum, minimum. You can save this or you can plot this. It says any node, it is working like that, or the trend of the stress on the selected node are like that. So you can always have a custom-made result here as well. All right. All these options, as we said, could be done for displacement as well. So we can define displacement plot as well. We can define strain plot as well. Now, there are two other options where it is not included in our training session. Then next stage for us is to find out about the effect of, let's say, mesh density on the result. Now, the good thing about the SolidWorks simulation, you can do the same analysis at the same time just by clicking and duplicating this and call it dense mesh and click OK. Everything is now being transferred and duplicated. The only thing we would like to change is the mesh size and the element size. So get back to create mesh and then open up the communication box, and then here we put from the very fine mesh to a coarse mesh, where now the element size is 11. Now click OK. You can see much coarser mesh we have here. The rest would be the same thing, and the only thing is just to run the study. When we run, now we can see the values of stress is getting changed. 408, and here we have different value, 402. The stress value is being changed. That's also appearing on the values of, let's say, displacement, which is 1.432, and here we have 1.435. So this is simply showing us having appropriate mesh sizing will define the final result accuracy. So it is always recommended when you have a simulation to run your case with the different mesh size, and when the results are getting stabilized in the terms of displacement and stress, then your actual model is mesh independent. Alright, so this is almost finishing our case study, but the only thing remaining is the comparison between what we found in the software to what is with the analog of with the hand calculation. In a course study where we used 1,173 number of elements, we found the maximum one misses stress as 402.589 and maximum displacement as 0.14 something. For the defined analysis, that value is 408, and with the finer mesh it will come to 415.605. So which one is more accurate? Again, when the result of the displacement is getting stabilized, then that is more accurate result. Compared to its analytical way, where we simply can find the normal stress and find the concentration value, and we can find the analytical stress around 409.87 megapascal. So in comparison with what we get is simply coming with the idea of we are just about less than 1% off the hand calculation. Alright, this is basically finish our case study here today, and the last thing I would like to mention is about the seats of simulation we have in SolidWorks. The basic license we have will cover the static analysis and the motion analysis, and the next level of the let's say simulation seat we have, which is called SolidWorks Simulation Professional Seats. You're able to do what you can do in SolidWorks Simulation, plus you can perform fatigue, thermal, frequency optimization, drop test, buckling, pressure vessel, 2D simplification, and sub-modeling study. And the next stage, which is the full license we have, is SolidWorks Simulation Premium, where you get all this option plus nonlinear static, linear dynamic, composite, and nonlinear dynamic as well. We also have the flow simulation seats, which is separated here. For those who are really interested to communicate more about the seats available and how we can provide these seats for you, you are more than welcome to, let's say, contact me. Just as a reminder before we finish the session and go to the question session, is the series of webinar with the registration link. If still you haven't received them, please send us an email and we will provide the registration link to you. I would like to thank everybody for listening. Again, my name is Esfandiar Kuhi, and this is my email address at Intercad.